Have you ever wondered what dictates the sharpness or selectivity of a circuit, especially when tuning into a radio station or filtering out unwanted frequencies? It is a fundamental characteristic known as bandwidth. In a parallel RLC resonance circuit, bandwidth directly measures the range of frequencies over which the circuit's response remains significantly high, typically above 70.7% of its peak value. It quantifies how selective the circuit is to a particular resonant frequency. A narrower bandwidth indicates higher selectivity, meaning the circuit responds strongly only to a very specific frequency, while a wider bandwidth implies it accepts a broader range of frequencies around resonance. The core reason for this relationship lies in the interplay between resistance, inductance, and capacitance within the parallel configuration. At resonance, the inductive and capacitive reactances cancel each other out, leaving only the resistance to determine the impedance. However, as you move away from the resonant frequency, the reactances no longer cancel perfectly, causing the circuit's impedance and current to change. The quality factor, often denoted as Q factor, is crucial here. It is inversely proportional to bandwidth, meaning a higher Q factor results in a narrower bandwidth, and conversely, a lower Q factor leads to a wider bandwidth. The Q factor itself is determined by the ratio of the energy stored in the reactive components to the energy dissipated by the resistor per cycle. To practically determine the bandwidth of a parallel RLC circuit, you typically calculate the difference between the upper and lower half-power frequencies, also known as the 3 decibel points. These are the frequencies where the current through the parallel RLC combination drops to 1 divided by the square root of 2, or approximately 70.7%, of its maximum value at resonance. Alternatively, you can use the formula that relates bandwidth to the resonant frequency and the quality factor, where bandwidth equals the resonant frequency divided by the Q factor. Adjusting the resistance value in the circuit is the most direct way to control bandwidth. Increasing the resistance generally lowers the Q factor and widens the bandwidth, while decreasing resistance narrows it. An interesting insight is understanding the damping effect. A low Q factor implies significant damping caused by higher resistance, which spreads out the circuit's response over a wider frequency range. Conversely, a high Q factor, resulting from lower resistance, means less damping and a sharper, more defined resonant peak. This principle is vital in applications like communications, where precise frequency selection is critical, such as in radio frequency filters, which use high Q circuits to isolate specific carrier waves. Understanding the relationship between bandwidth and parallel RLC resonance empowers you to design and analyze circuits with precise frequency selectivity. By manipulating the component values, and thus the quality factor, you can tailor a circuit to either sharply filter a single frequency or embrace a broader spectrum, providing versatile control over frequency response in various electrical engineering applications.